If you had told me as a kid that I could build my career around my favorite food, which was back then and still is ice cream, I would definitely have signed up for it. Our next speaker even obtained his PhD with a thesis on the structure formation in ice cream, but he did not stop there. As scientific director of the renowned Yili Innovation Center in Europe, he is now driving innovation in the entire dairy industry and shaping the future of food processing and product development. Today, the editor of the International Dairy Journal will give us exclusive insights, will show us how to thrive in food product innovation by minimizing flop rates with the help of artificial intelligence. Please give a warm welcome to Matthias Eisner.
Thank you.
The stage is yours.
Thanks.
Enjoy.
Thanks a lot. So, welcome to this talk, and I want to cover a couple of approaches we are using to reduce flop rates in product innovation and to accelerate product innovation in the food industry. And we do this by using AI. So if you are looking at flop rates, then you consistently find statements that somewhere between 70 to 90% of all products launched fail in the consumer goods industry. And this number is relatively consistent over the last decade, so you don't see a lot of change going on there. If we zoom in the phase after launch, then we see that the flop rate is consistently lower, which means that a lot of the stop projects, products not even making it to the market, a lot of this goes wrong in the early stages, where you start from development and to preparing a launch. And then once it is launched, yes, there are also flops, but these are consistently lower in numbers. So this is why I want to focus on the early stage, where we're really developing new products, developing new recipes now, and to walk you a little bit through what we have been doing there over the last couple of years. So if we do look at product development in the food industry, very typically, example of an ice cream, we have a bunch of ingredients, we mix them together and we formulate our product. And usually it's not one or two ingredients, but it's quite a number. Though the traditional approach, what you learn at university is, you have these ingredients, you do a full factorial statistic design of experiments, and then you run your trials, you determine where your optimum is, and this is your formulation. This is great in theory. It starts failing if you're dealing with 5, 10 or 15 ingredients, because then your factorial design becomes so multidimensional that you end up with hundreds of trials, and nobody's going to do this. So how real life works in the food industry is much more, we have experienced product developers. They have been doing this for 10, 20, 30 years. So they know their formulations, they know their ingredients, and they start writing down a best guess recipe. Then this recipe is tested in the lab, in the pilot plant, sometimes in the factory. You get results, you learn from this, and then you go into a new cycle. And very often along this, we have results from other projects which we did earlier with not exactly the same product, but something similar. We get external advice from suppliers, from experience in the factories, and we mix this all together. But end of the day, it kind of stays an educated guess, which we are iterating and iterating. And the question we had is, on the one hand side, with a change in people in the companies, we have less and less of these very experienced developers who have been doing their job for 30, 40 years and know everything by heart. So we want to capture this knowledge and make it available for the company when they retire. But also, we're looking for ways to make this circle faster and more efficient and a little bit less trial and error. And I want to start with a case study. I won't bother you with the technical details, but we have been working on whipping cream, and whipping cream is a, if you look at the markets in Asia, a highly stabilized product. So you have fat, protein in there from the cream, of course, but you have a lot of emulsifiers, stabilizers. You have a couple of parameters in the processing with the heating and homogenization. And you have a lot of product characteristics you are interested in. And of course, it should whip, but then it should be stable on a cake. It should not sink into a tea when you put it on tea. Yes, they are doing this in China. And it needs to be stable over 9 months and longer. And so you have a lot of parameters there, and we did lots of pilot pen trials for this. Though this is essentially how the data looks. On the left, I walk you through, you have a couple of the parameters of the process and when we did it, so there's seasonality hidden in there. You have fat content and these things in there. Then we have what we call the recipe. So that's a mix of all the stabilizers, emulsifiers and all the other ingredients we put in there. And one of the things you are seeing is there are a lot of zeros because you're only selecting few ingredients out of your total selection and all the others are not added, so they are 0. And then you get a matrix which is highly sparse, and this is very hard to handle with statistics. So statistics typically don't like matrices with lots of zeros because that's relatively tricky for the standard models. And then on the right hand side we have everything we measured on these samples, and we do this over time. So if each of these small boxes is a time point, but what you see is, yeah, sometimes it's Christmas and that was done in New Zealand. Nobody's working over Christmas in New Zealand, and then you don't have data for a month. Sometimes you have a formulation which is simply not working, and you see this after 2 or 3 months. And there's no point keeping testing it for the other 9 months just to generate data for the model. Obviously this is simply stopped. And some at the bottom are there's no data yet because the trial is still running and the samples are still in storage. And we were looking for a way how to make sense from this data set. And this is where we came into AI or machine learning, which hopefully would be able to address all these challenges of a lot of zeros, missing data. There's a time series in there which is not quite easy in statistics. We have some inputs, some recipe parameters have a lot of variation, others have very little variation because we don't do statistical design. And we were looking into, can we split this up? Quite simple. We took process and recipes our input, what we measured is our output, and we want to have a model in between. Now with all these missing data we have in there over time, we had to look for a method where we can fill up this missing data to actually build a meaningful model. So we kind of built in a loop in there where we use imputation to create a part model which fills the data and then uses this to extend the model step by step. And I'm an engineer, I'm interested in getting this working. I'm not interested in the mathematics or informatics behind. So we were looking for a partner to do this with us. And that's Intelligence, that's University Cambridge, Cavendish Labs spin-out company. They are very good at all the modeling and the mathematical side, and they supported us greatly on this. What I want to show you is what we learned from it, and that's we typically got these plots with correlations, and we can learn a lot from it. So you see yellow, green is where you have high correlation between input, so your ingredient, and the output, your whipping cream performance, and the dark violets are low or no correlation. And that immediately helped us to kick out a lot of the ingredients we have been testing, because apparently they don't do anything in our product. So why keep testing those? So we could simply reduce the number of trials and the whole ingredient set we were using quite strongly. Also, and that was very interesting, we found no variation in parameters where we would have expected it, like fat content. And then when you go back to your data, you see there was hardly any variation. The model couldn't learn anything about influence of fat content in this case. And this is why it still needs a dairy expert or a product expert to look at it, to really check are these predictions meaningful or not, because the model just looks at the numbers. It doesn't know anything about meaningful. The really great result from this is that we were not able to predict the performance from the recipe itself. But we were able, if we had the recipe and the analysis data after the first month, we have been able to predict all the rest of the 9 months. Which essentially means we don't have to wait 6 or 9 months before we can learn and do the next cycle, but we can already do this after 1 month. Which means you can in the same time run to 6 or 8 times more circles in this trial on error circle. And that greatly sped it up. We can also use the model to predict, of course, best recipe candidates in there. And so that was a very nice outcome, especially the prediction over shelf life. I've mentioned the fat content here, and this is really, it needs a critical eye of a domain expert to look at this data, because otherwise some of the predictions are very good, some are unexpected, and you really have to dive into the unexpected. So I would not think that models are yet in the state of acting autonomous alone without supervision. You still need the expertise, and this is why we need all the training for dairy experts globally, so we still need the product developer actually with his knowledge to some extent, but we can help him a lot. Another question we were interested in is, does what the model predict actually make physical sense? So can we replicate what we know about a system technically? Does the model also learn this in the correct way? And we have been looking at ice cream for this case. Again, I don't bother you with all the details, but one of the very important properties of ice cream is how fast it melts. So if you want to have it keeping its shape and not melting away very fast. And one of the key parameters is how strongly the fat structures in ice cream are developed. And so we have been running a couple of trials, surprisingly little by the way. And we have been separating this into seeing, can we predict some of these properties we know from the recipe? On the left you see, for example, how solid the fat is depends on the blend of fats. And the model can predict this pretty well from a blend of fats. You get a more or less perfect correlation. Yes, this is what you can expect because you can do it on paper in 2 minutes yourself. But it's a very good check for a model to see if it is actually physically meaningful. And the same is on the right hand side. We see that the degree of fat structuring correlates very well with the melting rate we find. Again, we knew this before, but we did this as a test to see if the AI model, if they actually come up with meaningful physical predictions. And yes, this works here. And that's a great example, and the learning here is also don't try to go from all the way in one step, but split it up in pieces and make smaller steps in modeling, because this makes it much easier to validate each step of the modeling rather than going from your recipe to the final product in one go. And then from this we can get these nice plots, but essentially they tell us for each ingredient we have been using, does it help to improve meltdown to the right, or has it an adverse effect to the left? And from this already you can pick your ingredients and you select your the right ones, but you can also exclude some which have been sold to you with a promise to be beneficial, but they actually destroy the structure more than they help. And that's also, you can dive down into mechanisms quite a bit if you like to, and that was surprising for us because very often you hear AI models, they are kind of a black box and you don't know what is happening in there. No, if you have the right tools and you can dig down and you split it into components, you can actually understand what is happening in AI models. The third case, and this is very much related to consumers. we are developing a lot of most of our products for consumers, and consumers have to like them on a taste and perspective and on a sensory perspective. They don't care about the ingredients and the technology. They only look, do I like the product? Does it taste good? Does it taste good enough to buy it again? And very often when you see how market research is being done, people ask consumers, what do you like about the product? What don't you like the product? Should it be a little bit sweeter? Do you want to do a bit more salty? And this is how typical market research goes. And we have been doing this for cheese. We have been doing the consumer market research, but we also had expert panels in there. And then we have been looking on, can we correlate what consumers tell us with what the trained experts panel tells us? Because the experts, they are really trained to tell you on a scale from 0 to 10 how sweet a product is, and they will relatively consistently score a certain yogurt at 7.3. Whereas consumers, the answers are all over the place. And one of the interesting things is when we started correlating, you see a couple of pretty good correlations. So bottom left is color. Yes, you expect that consumers can judge the color of a cheese right. Fine. Similar for hardness, expert judgment for hardness, although this is how hard it is when you squeeze it. It's quite similar between consumers and our experts. But then we see a couple of others, and this is the mouthfeel. And the consumers judged the mouthfeel of cheese different based on its color. Which is intuitively right. I mean, it's like for cheddar, it is known that darker cheddar is perceived as more intense. But it also tells you what consumers give you as feedback doesn't have to be right. Because if we would have trusted this, we would have started adjusting the structure and hardness of the cheese rather than adjusting the color, which is what they actually wanted. And if we go further, and we did this also on tastes, then you see, for example, these were Chinese consumers. They pick up sweetness pretty well, they pick up bitterness pretty well, so this all works. But then you have a couple of parameters in there which are totally off. So what consumers describe as sour is actually umami. What consumers describe as bitter can also be salty. And what consumers describe as salty can actually be sour. And this makes it very difficult if you ask consumers, do you want the cheese a little bit more salty or not? And they say, I want it more salty, but they mean I want it less umami. It makes product development extremely hard. But by having these insights, we can now actually not telling consumers they are wrong in what they are saying. That's not the point. It's about if they tell us we want it more sour, we can go back and say, hey, maybe they mean salty. So let's try a bit less salt or a bit more salt to tune what they believe is sour. And this is a great tool for us to deal with these complex data sets, because consumer science has a problem. It's you have lots of different data, but our senses are not linear. Though our senses are intrinsically non-linear, they have threshold values, they have saturation values in their response to certain molecules. And if you go do this with linear statistics, it's wrong by definition. Whereas here we can do it in models which are intrinsically non-linear and mimic how the senses work in a better sense. And with this we can tune our product and recipe directions much better. So to sum it up a little bit for you, we have seen that AI machine learning can be very useful, especially in complex and big data sets. But surprisingly, we have found that if you have good quality data, you get away with very small data sets. So we had examples where we have done 15 recipes and we could build a model on this. Yes, not in the most complex cases, but if you have a constrained domain, you can get away with good quality data and quite little data, and that's interesting. And you need to keep validating this. So you need to keep asking yourself, is what the model predicts actually useful or not? Can it be right, or do I look at an artifact? And you shouldn't extrapolate too far, but that's generally for machine learning. The big advantage we have if we do product development, we are not running nuclear plants. So the risk of a wrong recipe is actually pretty low, because if we have a recipe which is wrong, we take it to the pilot plant, we try it, it doesn't work, fine. So we can always test it with relatively low effort and risk, but it makes it much more efficient to come up with a good promising candidates. Could all this be done with statistics? Yes, probably. If you really want to, you can do it in a statistics package. But some of these cases have taken us 1 or 2 days to set up and to do the modeling and the analysis and the deep dive into the model, where with statistics it would probably have been a couple of weeks' work. So there's also benefit in doing things quicker and more easy and more user-friendly than a traditional statistic package. And the other surprising outcome for us is really we can learn something mechanistically about it, and that's something we didn't expect in the beginning. We were expecting kind of this black box, and now actually we are using it to help us understand how our food systems works, and this is quite a nice outcome as well. So thank you for this, and I hang around a little bit in case of any questions.